To better understand how surge protectors work and learn how to use them in installations, we need to start from the beginning, with the types of surges and their causes. A power surge is one of many electrical disturbances that can occur in the connecting cables between individual devices or their modules. Disturbances in the form of transmission distortions or temporary transmission interruptions are mostly caused by the quality of the cabling and the durability of the connections. Interference in the form of overvoltage may result from the operation of connected devices or associated equipment, but manufacturers of individual components and developers of complete installations usually anticipate the elimination of such adverse phenomena at the design stage. Another and more dangerous source of surges is atmospheric discharges, which affect electrical and electronic installations in many different ways. Sabotage, caused by the deliberate use of high-voltage generators or power lines, is also a possible source of surges. Individual sources of overvoltage, the hazards they pose, and ways to counteract them will be discussed in the following sections. Direct lightning discharge. This is an electrical disturbance originating directly from lightning, ranking highest in the hierarchy of possible hazards. It is a surge with very high energy. Atmospheric discharge is the result of a potential discharge between clouds and the ground. It is divided into two stages. The preliminary discharge, which we see as fractals, prepares the path for the main discharge. The main discharge is a very short impulse that occurs in a very short time and has enormous destructive potential. The flow of lightning current creates an electric arc, the temperature of which can exceed the temperature on the sun. In a fraction of a second, it heats the air around it, generating high acoustic pressure, which we hear as thunder. Lightning current spreads across the surface of the Earth, generating a step voltage that can reach tens of kilovolts per meter. It is particularly dangerous for animals and people in the vicinity of the lightning strike. Direct lightning strikes pose the highest level of danger to buildings, human life, and electrical and electronic equipment. They generate voltages of several million volts and are characterized by current flows of up to several 100,000 amperes. The flow of total lightning current through building structures creates a fire hazard and has a destructive effect on all electrical installations or other structures that can conduct electricity. A direct discharge to a building involves the flow of an impulse current of up to several 100,000 amperes. The high energy in the lightning channel triggers high temperatures, which can cause a fire. Exposed electrical installations or metal components may allow partial lightning current to enter the building, posing a serious threat to people and all installations inside the building. This can damage electrical and electronic equipment, such as antenna installations, security systems, lighting and air conditioning systems, and structural telecommunications networks. The only way to eliminate the effects of a direct lightning strike into a building is to use a properly designed and constructed lightning protection system. The conductors of this system provide a path for the lightning current to flow to the ground, limiting the flow through the building structure. This reduces the risk of fire, but does not eliminate the risk of damage to equipment located outside or inside the building, as the amount of energy discharged to the ground by the lightning rod is approximately 50% of the total energy of the lightning strike. Electrical installations located outside are still at risk of partial lightning current, and lightning conductors increase the risk of damage to electronics from electromagnetic pulses, which we will discuss later. A direct strike on an overhead power line poses a very serious threat to a building, even though it may occur at a considerable distance from it. A direct strike to an unprotected power line can cause a very high surge current to enter the building. High voltage causes the insulation of electrical cables and connected devices to break down. This can result in electric shock to people inside, damage electrical equipment, burn through cables, and even cause a fire. A way to limit the effects of discharge in the power supply line is to use coordinated surge protection in accordance with the harmonized EN 62305 standard. The use of surge protectors reduces the surge voltage to a level that is safe for electrical equipment. Protection solutions for overhead power lines require individual designs, depending on the size of the buildings, the location of local switchboards, and the length of the cables. This is necessary to ensure that the main surge currents and secondary surges generated after the main surge protector has been activated do not pose a threat to the installation. Proper surge protection should be divided into several zones, taking into account different voltages and sources of surges, including surges caused by electromagnetic pulses. The effects of a lightning strike can be minimized by using a lightning protection system. Depending on the impedance of the lightning protection system and the impedance of the grounding, components located close to the lightning protection line will still be exposed to partial lightning current. Partial discharge occurs when the main lightning current is not directed to a particular installation, but a spark jumps to that installation as a result of high voltage. Then, part of the lightning current is divided and flows through a section of that installation. The magnitude of the partial lightning current is unpredictable because it is the result of many different factors. The inherent impedance of the lightning protection system and the impedance of the grounding cause a potential to build up relative to the ground, which increases with the length of the cables. When the sum of the voltages is higher than the breakdown voltage of the installed device, a spark jump occurs and a partial lightning current flows through the installation. When installing devices outdoors, it is important to maintain an adequate distance from the lightning rod. This distance must be greater the higher the electrical equipment or other installations are located on the building. Many factors affect the distance of the device from the lightning conductor, so it is recommended to perform calculations taking into account the lightning protection class, the insulation of the installation, and the number of grounding points of the lightning protection system. The greatest risk is for devices installed on roofs, so the recommended distances from the lightning rod can be as much as several meters. By using appropriate surge protectors, we eliminate the risk of lightning current entering the building. They redirect the flowing current directly to the ground, which prevents damage to equipment inside the building. To protect outdoor equipment, its housing must be connected to the grounding of the surge protector, which will minimize the effects of voltage between the housing and the cables. Such surge protection must be resistant to partial lightning currents, and therefore must be tested in accordance with Category D1 or D2. When lightning strikes the ground or protruding objects, such as trees, poles, or buildings, the lightning current spreads close to the ground. Since the ground has high impedance for large current surges, a dangerous step voltage is created on its surface, posing a threat to animals and humans. This voltage also occurs between individual buildings and especially between locally grounded points. This potential is also very dangerous for electrical and electronic equipment, as it can be equalized through underground installation cables and the individual devices connected to them. Multi-point electronic systems spread over a large area are particularly vulnerable. These include measuring systems, video surveillance systems, alarm systems, and automation control systems. This is a case where the hazard does not come from the cables, but from the ground. There are several ways to avoid ground potential, and the most effective one is to install a potential equalization system. This solution reduces the effect of step voltage and limits the risk of electrical breakdown in connected devices. Potential differences between buildings will be relatively low, because the current is equalized by PE conductors with a large cross-section. It should be remembered that the potential equalization system may have a fairly high impedance, which depends on its length. Therefore, in some cases, electronic systems that use low voltages for transmission will still be at risk. As additional protection, it is recommended to use surge protectors to eliminate the risk of potential difference loops being closed by electronic components. Sometimes it is impossible to install an equipotential bonding system due to the size of the system. In such cases, the surge protection used should be resistant to partial lightning currents, and therefore tested in accordance with categories D1 and D2. Another, or additional way to avoid surge is to use galvanic isolation between individual devices. Such isolation prevents surge current from flowing through electronic components, as there will be no loop closure through which the potentials would be equalized. Another advantage of using separation is the elimination of transmission interference that occurs as a result of potential differences not caused by atmospheric discharges. Popular systems where separation is used as standard include Ethernet networks and devices that meet industrial standards. However, there are many systems on the market that do not have built-in galvanic separation as standard and require additional separation. It should be noted that the effectiveness of separation is limited to a maximum of several kilovolts, so it is safest to use it in combination with surge protection.